Peoples.
Exponential functions, yes.
All right, so an exponential function is one in which the base is a positive constant, greater than 1, and the exponent contains a variable. So it looks like this, where a is not equal to 1, and it's positive. Okay, so here we have f of x equals 5 to the x. And evaluate the following and find approximate values where appropriate. Okay, so f of 0, well, we know what that means. That means plug in 0 for x. So 5 to the 0
which is
1. Ta-da. Okay.
So here equals 5 to the
negative 2.
What did negative exponents do? They make things negative, right?
No.
Oh.
They will always put them in the denominator. So this
1
is
over 5
1
squared.
over 5 squared, which is 1 over 25.
There you go.
All right. This one, we've got this equals 5 to the 0.5.
Now, that's kind of cool because what is 0.5 the same as?
1/2.
Oh, what's fractional exponent?
Square root of 5.
There you go. See, this is old stuff.
All right, and then we have 5 to the pi.
Which,
okay,
that's it. What is pi?
3.1415.
Yeah. So that's about 5 to the 3 point something. So that becomes, if you want a real number, that's about 156.993 for rounding.
All right, but this is what we would ask you for. Okay.
Yeah.
All right, so here we go. Now that we've had a little practice warm-up, sketch each of the following graphs on the same set of axes and make a table of values. So I'm going to pick some values for x. I'm going to pick nice pretty numbers. I'm going to pick -2, -1, 0, 1, and 2.
Maybe try 3 too.
Yeah, 3 just for grins. And let's see, we've got 2 to the x power. So 2 to the -2 is 1/4. You should know that. And then 2 to the -1 is 1/2. And then 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8.
Now we're going to go plot those points. Now let's pay attention to what you just did. You just figured out that when x is -2, the y value will be 1/4. Okay, so that's really close to that.
Kind of like right there.
And when x is -1, the y value is 1/2. And when x is 0, the y value is 1. And when x is 1, for this function, the y value is 2. When x is 2, the y value is 4. And when x is 3, the y value is 8.
All right.
And so you can see the points, and we're going to try to sketch it.
Oh, goodness.
And it's so hard to do.
It should get closer, but...
That's good enough. Yeah, and it would get closer to the x-axis. Eventually, you could probably see if we did something like 2 to the -100, that would be super, super, super close to 0. So that's the point. Now, let's look at the next one. All right, so this is, I'm going to probably write it. Yeah, it gives 1/2 to the -1, -2, I mean.
-2.
Which is actually, you know what, let's do something kind of interesting. Let's go up here. And let's write up here that 1/2 to the x is the same as parentheses 2 to the -1
to the
x, which is the same as 2 to the -x. So now 1/2 to the -2 could actually be thought of as 2 to the 2, which is 4.
So if we go ahead and use that reasoning all the way down, 1/2 to the -1 would be 2 to the first. Which is 2. And then 1/2 to the 0, well, we really don't have to do anything to that. We can just go ahead and say that's 1. And then 1/2 to the first, oh, that's easy too. That's 1/2. And then 1/2 squared is 1/4. That's easy. And then 1/2 cubed is 1/8. You should know that. So if we graph this at -2, x equals -2, we've got 1, 2, 3, 4. Right there.
Ooh, let's do 1/2 to the -3. Let's
-3.
just add that.
So
yeah.
1/2 to the -3. Oops.
Put a negative sign there.
Yeah, there was a...
It's just hard to make it.
There we
There's
go.
a negative sign.
And that would be the same as 2 cubed, which would be the same as 8. So if we did to 3, 4, 5, 6, 7, 8, right there.
Hey, that seems to be reflecting across the y-axis there.
Yes, it is.
In fact.
It really is. That's 1/4. And then 1/8, which is getting really close. So, if we graph this, okay.
Let's pretend it goes through those dots.
And it doesn't come back up, guys. It doesn't do that. It just comes closer. Okay, whatever.
But the really point thing, maybe in green, notice that, circle that function there, 2 to the x, and over here, 2 to the negative x, look what they do.
They flip. Remember when we did transformations of functions earlier last semester, we talked about when you multiply the negative times the x, it reflects across the y-axis. Well, that's what we're doing here.
Yeah, we're negating the x, but keeping the same y.
Okay, so what you need to do is go to chapter 5, section 5.2 in your textbook and work number 14.
And that's not using a calculator.
Yeah, it's just sketching a graph, okay?
Just
you
like
can
we
use a
just
table. You can use a table just like we did.
Yep.
Okay.
So, if you notice, both of these graphs have y-intercepts at the point 0, 1. That's a standard of exponential functions where the leading coefficient of the function is 1. But these are, if you'll notice the graph on the left that Ms. Meller is right now drawing the little asymptote to, this is called an exponential growth function because as x gets bigger, y is getting bigger. And next to it, this is an exponential decay function because as x gets bigger, y is getting smaller.
Okay, and if you notice, we have this really cool thing that exponential functions do. We have horizontal asymptotes. Remember when you divide and keep dividing, you're never actually going to get to 0, and that's essentially what's going on in these graphs, especially this one. We're dividing and it's never going to get to 0. So we have a horizontal asymptote, which we talked about in radii, and it equals y equals 0. That's your horizontal asymptote.
And that's what this notation here means. As x goes towards negative infinity for this graph, y gets close to 0, and as x goes towards positive infinity for that graph, y gets close to 0.
Okay. Now there are no vertical asymptotes in exponential functions. I know it may look like it here, but that's not the case. It's going to keep getting bigger.
Forever and ever.
Forever and ever and ever. Yeah. Okay. So here we're going to compare the rates of growth for the function f of x is 2x to the x and g of x is x squared.
And notice that she's graphed the f of x equals 2 to the x is in red. So our exponential function is in red. And, oops.
I got to find the red marker. Hold
Yeah.
on. Not it. There we go.
Exponential function's in red, and the power function, quadratic there, is in blue on the graph down here. So what we're actually looking at is what is happening to these functions if we change the window. Now in this first graph on the left, notice that the x goes from 0 to 3 and the y goes from 0 to 8, and you'll need to draw this graph and also label it in the boxes provided in your notes. But notice that if you look at this graph, it appears that the quadratic graph, the power function, is going to increase more rapidly because at some point it goes over that exponential. But let's zoom out a little bit. Now our window is for x is 0 to 6 and our y is 0 to 25. And if you notice, there's this little area in there where you can see that the exponential function dips below, but then it appears to intersect again. And if we go out even more and look at the next graph, this is from 0 to 20 for the x and 0 to 1,000 for the y. Notice that you can see, ooh, you know what? That's not 0 to 1,000.
No, that's 0 to 25.
We put the wrong graph in right here. You know what that one would look like? Here, just below it, just sketch it real quick. Did you pause it?
No, I didn't.
Okay.
Okay.
We're going to kind of draw a little sketch of what it should look like. You can go to your calculator and draw it. But in the graph, what's going to happen is
Okay, so the blue one.
the blue one is going to look like this. It's going to look almost like a line on that scale. Not going to see much curve. But the red one, the power function, is going to do this. And you can see it is really increasing rapidly.
And there's 2 points of intersection, as you can see.
It's just that you don't see it on the bigger scale. But
yeah.
Anyway, that's that.
Okay, so find the exponential function which passes through. All right, remember this is a standard point on all exponential functions with a coefficient of 1. So we're going to say, all right, well, let f of x equal a to the x.
And yeah, and here it says, let's sketch the graph first. So let's plot that point 0, 1 on there and estimate where 2 and 16 would be.
Okie dokie.
Yeah, you don't probably need to, oopsie, count 16 up there.
2, 4, 6, 8, 10, 12, 14, 16. There we go. We'll just do it like that and come down here, and there's the 1.
And if you connect those two, not with a line but with a curve, you can see that what's going on, it doesn't go below the x-axis, but it's hard to do that on the slate. So it looks like this. Okay?
Okay, good effort. Okay.
2 and 16, yeah.
Yeah, 2 to 16. All right, so if f of x equals a to the x, remember y is the same as f of x, so 16 equals 2 to the x. Well,
a to the 2. A
Oh.
to the 2.
Oh, I'm sorry.
It's okay.
I got excited.
Yeah, because we like 2s a
All
lot.
right, so the square root, I can square root both sides. Okay, so square root both sides, and I get
Plus and minus 4.
a equals plus or minus 4.
But what's our rule for exponentials?
A has to be greater than 0.
So we have to throw out the negative one, and a is 4. And now we're going to write the function f of x equals 4 to the x. Boom. There we go.
All right.
Let's go to this next one. We're going to do the same thing, at least plot the points. 0, 1. That one you might want to make bigger because look at the y on the next one. So we're going to increase our scale here. 0, 1. And then negative 1 and a third. Well, that still appears to be an exponential function that's increasing, doesn't it? See, as x got bigger, my y got bigger. Just like in the last one, as x got bigger, the y got bigger, so we have to be increasing. So again, we're going to set up our general formula, a to the x, and in this case we know that when y is 1/3, x is negative 1, and an easy way to do this is to think about what, let's not do it that way because that they can always do that. Let's do a clever way. 1/3 equals a to the negative 1.
Oh, I see what you're saying.
Yeah, you know where I'm going. Hey,
Okay.
if 1/3 equals 1 over a, guys, what is a?
A equals 3. Boom.
Yeah, and so this function is f of x equals 3 to the x. Now, of course, what Ms. Miller started to do, which was to raise both sides to the negative 1, you can do that. But sometimes it's a good idea to look for little patterns.
Mm-hmm.
Okay, now we need to go back and remember all of our translations and things that we needed to do. So if we know what the basic 2 to the x looks like, and you should because that was the very first graph we sketched a few slides ago, okay?
With the table.
With the table, that's right. So what does letter A say we need to do? It says we're going to take our 2 to the x and do what? Shift it up 1.
Up 1.
Yeah, when that number is after the actual function with the property, the 2 to the x, the exponential thing, then we add to it. So we're going to shift. So our original graph, if we sketch our original graph maybe in dotted line, she's sketching right now what 2 to the x looks like. And maybe put a 1 here and a 2 there. Yeah. Okay, that is f of x. That's our parent function. Okay.
F of x equals 2 to the x.
That's our parent function. And so what is g to the x going to do? It's going to take that graph and shift it up 1.
So this point goes here. This point is going to go here. And the 1/2 is going to go to here. All right, so now it's going to look kind of like that.
Now, yeah, and here's a way to think about this. Let's just make a few coordinates here. Actually, let's just write them as coordinates instead of a chart because we can do something cool with it. Let's write this as 0, 1. When x is 0, y is 1. In the new one, we're going to add 1 to the y coordinate. So now when x is 0, y is going to be add 1 to that too. All right, go to the next one. When x was 1 on this, the y coordinate was 2. So now it's going to be the point 1 and add 1 to the y coordinate. Now, if you actually think about your transformations this way, when we get to some graphs that are a little more complicated, this is the easiest way to think about them.
Okay.
All right, so again, she's going to go ahead and sketch in dotted, the blue dotted, the 2 to the x graph. And while she's doing that, I will talk about the function. Notice the function says negative 2 to the x. So what does the negative in front of the term do? Well, you should remember, just like with negative slope, it makes it negative, so it's going to take all those y values and negate them. So there's our parent function, and then our real function is going to take the y values and negate them. So 0, 1 is going to become 0, negative 1. 1, 2 is going to become 1, negative 2. And that point, which is what, negative 1/2?
Yeah.
1/2? Negative 1, 1/2?
Is negative 1, negative 1/2.
Yeah.
So it looks like the mirror image over the x-axis.
Yeah, and just sketch out the points we just used real quick. 0, 1
So,
became 0, negative 1, because we're going to negate the y-coordinates. 1, 2 became 1, negative 2, and negative 1, 1/2 became negative 1, and we're negating the y, negative 1/2. Oopsie.
Ran out of space.
Ran out of space. Anyway, hopefully you get the idea. All right, now we're going to go to some that require a little bit more.
Okay.
Here we go. So this one requires a little bit more thinking, and what we're looking at is we're going to shift our parent function 4 to the right. So our point, if we look at our parent function f of x equals 2 to the x, our point 0, 1 is going to become the point 4, 1. Now look back up here. When we plug 4 in to that function g, notice that 4 minus 4 is 0 and 2 to the 0 is 1. So what is going to happen is we are going to shift our x values 4 to the right but keep the same y value. So on the parent function 2 to the x, the point 1, 2 is going to become, all right, to have the same y value, we're going to have to shift the x coordinate 4 places. So it's going to be 5, 2. All right, what happens if we do negative 1 and then we know on the parent function that's 1/2? In order to have the same y value, I'm going to have to shift that negative 1 3 places. 5 places, 4 to 3, whatever.
4 places.
Okay, so now you can see what the graph should look like. Once again, just real quickly without doing our scale tremendously, there's our parent function right there. Okay, and now let's look at that point 0, 1. That point 0, 1 right there is going to come over here, and it's going to become the point 4, 1. Okay, and this point 1, 2 is going to come over here and become the point 5, 2. So you can see what is happening is going to look like that. So it has the same shape as the parent function, but it gets shifted to the right. And what do you think is going to happen here with our last one?
Oh boy, well, if you know that adding 2 to the x value is actually going to shift the function to the left 2. Okay,
and
it's going to shift up 3 because of the plus 3.
All right, so let's do our little points over here again. The point 0, 1 is going to become, now we're going to shift left 2, so go negative 2. And the y-coordinate when we do that is going to go up 3 from what we had. So 1 plus 3 is 4. Okay, the point 1, 2 is going to become the point shift left 2, so that goes to negative 1, but the y-coordinate goes 3 above the one that it had. Okay, and the point 2, 4 is going to become the point, so it's left 2, ooh, a y-intercept, 0, 7. So that graph is going to look like this.
So we had
the parent function, yeah.
Oh my goodness.
Okay.
Whatever.
Yeah. And
okay, well if that's 1.
7's way up there.
Okay.
Let's just
7's going to be really high. All right, but anyway, it's going to be the same general function, just shifted up, and left. Oh, it's got to keep going down.
Yeah.
Until it gets to it shifted left to.
Yeah.
So like that.
So it's not all squiggly looking, but you can make it solid, right? Because that's the graph we actually wanted.
Yeah.
Ding, ding, ding. There we go.
And right here, we'll say right here, this line right here is the vertical shift, right? Because we shifted 0, our horizontal asymptote of 0, up to y equals 3.
So there's our shift.
And so this right here, well, our 0, 1 is now at negative 2, 4, which is like right there.
So.
All right, so this point moved there.
So when you do the problems on this, again, you are to do them like we did them. Don't get your calculator out unless you're just checking, but you really need to kind of think about them like we did, because that's how you'll be asked to do it in testing conditions.
Okay.
Okay, so now the graph of 4 to the x looks a whole lot like the graph of 2 to the x. All you really need is 2 points to get the general idea. We need the point when x is 0, y is 1. Yeah, and when x is 1, y is 4. That's pretty much all. You can see that this is going to be much steeper than the 2 to the x, but it has the same shape. And now all we want you to do and think about, the textbook wants you to think about, it stretches and subtracts and does all kinds of things by certain factors. All we want you to think about is here. If we have 4 to the 0.5x, okay, that's the same as 4 to the 1/2 x. And that 1/2 means square root. So it's really the square, no, it's the square root of 4 to the x.
Oh, I'm sorry.
Yeah.
Got excited.
Yes, the square root of 4 to the x. So the thing about this is that is going to make the graph stretched out, okay? It's a horizontal stretch. This is a horizontal stretch. Why? Because we are making the x's have to be stretched out more, all right? So letter B, this one, look at the difference between 0.4 and 0.5. That is still going to be a horizontal stretch. That means that we are going to take our x's, and in order to have the same y value, I have to have an x that's actually 2.5 times bigger than it really is, because 0.4 is 4/10, which is 2/5. So this one, you could see, where is that negative? You're going to reflect across the y-axis. And this one here, letter D, is going to reflect across the y-axis, and it's also going to be horizontally stretched.
A cruise.
A cruise. And if that were something besides decimals, like let's say it said 4 to the negative 2x, you would still reflect across the y-axis, but that negative 2 would actually make it get smushed instead of stretched out. We're not as concerned on this exactly with the complete. Yeah, we're more interested in the plus and the minus and that kind of thing. All right, so in this graph here, you've got the graph already shown, and so without graphing, describe the transformation.
Oh, I'm just multiplying by 3.
So the
this graph.
Yeah.
So all of the y values are going to be multiplied by 3.
So that's all you need to write. Y values multiplied by a factor of 3. He's
Give him that.
Now, letter B, what's that going to do? Well, we have a coefficient of -5. And so it's going to multiply the y values by a factor of 5 and reflect it across the x-axis. Now, this is a case where, remember how we said usually your basic graph has the 0.01 as your y-intercept? Well, if you go back to part A,
over the x-axis.
Over x-axis. Did I say y-axis?
I think so.
Okay, meant over x-axis. If you go back to part A, if all of the y values get multiplied by a factor of 3, now my y-intercept is the 0.03, not 0.1. And the y-intercept down here is the 0.0, -5.
Remember we talked about how 0,1 was like a standard for all exponential functions. Well, these have a coefficient, so you multiply it by the coefficient.
But notice we're still following the rule, which is that the base is a number greater than 0, greater than positive and greater. The other thing to notice here too as well is when you do your order of operations here, you do your 2 to the -0.8x first, and then you do the multiply. You don't do the -5 times the 2 and then raise that to the power. Okay, order of operations. Okay, now let's look at some. You're going to do this problem. Okay.
Use your calculator, but you must sketch the graph and label the window that you used.
Yeah. All right, so all of these now are going to be some word problems, and so it's really going to be, they're really simple. Your word problems are very simple, so don't be afraid of the couple that we ask you to do. If you invest $10,000 in a CD with an interest rate of 4% per year, the value of your certificate is given by this function. A of x equals 10,000 times 1.04 to the x. Now, the 10,000 there comes from the initial deposit, and the interest rate of, where do you see that 4% hiding? It's
right here.
Yeah, it's the 0.04 added to 1.
I mean, this is a CD. You want your money to increase.
Yeah.
So you 1 plus, it's 100% plus 4%.
Yeah, so we want all of the $10,000 to be in there plus 4% more. So that's what that means. So here, how much is the function of this? How much is the CD worth in 5 years? Let's use our notation properly. So that's A of 5.
Well, I'm going to just write x equals 5 because the 5 years.
And then
so A of 5
equals 10,000 times parentheses 1.04 to the 5. And now you just go get your calculator out and you get approximately $12,166.53. This is a case where we actually don't go to three places past the decimal because we're asking about money, you know. All right, now when will your CD be worth 18,000? Here's the thing. Later in this chapter, we're going to learn about logarithm functions that let us do this analytically, but right now your only technique is to use your calculator. So what we would do is graph the original function and, oops, go ahead and show it, that's good, and when is it worth, oopsie, when is it worth $18,000 is when y equals $18,000.
So what you can do is you can put in f1 of x, the equation, the a of x, and then in f2 of x you can write 18,000 because that's the function for the money, okay?
And notice your scale here. For those of you that are going to try, and actually you should do this on your calculator, notice that the x scale goes from 0 to about 25, I think. And your y scale, though, look at that, it goes up to about 30,000, okay? Which, of course, it would have to be something bigger than 18,000, okay?
And definitely bigger than 10,000. I mean, that's one scale. You can go ahead and say, oh, look, it's got to be bigger than 18,000, bigger than 10,000, etc.
Yeah, and see, there's your point. So the question, when will your CD be worth it? Look at that. Wouldn't you say about 15 years? You wouldn't say 14.9866, you know, you'd say about 15 years.
We're not going to ask you to convert that to months.
Yeah. We just want to know that you can get to the general idea. Okay, next one. Okay. Estimate the population of Tokyo, Japan in millions from 2000 to 2015 can be approximated by this function, where x equals 0 corresponds to the year 2000. A general note, whenever you have a problem involving years like from the year 2000 to 2011, you never let the 2000 be a number you substitute in. You always assign that year or whatever year you're starting at as time equals 0, okay, just in general. All right, so what are we really interested in here? If we're going to estimate the population in 2015, that means
x equals 15 because that's 15 years after 2000.
And so all we want to do is we want to see you're substituting in on your formula P of 15 equals 26.4 times 1.0019 to the 15th, and once again that's approximately 27.162. Now the important thing of this problem is, notice it says our population is in millions, so you would not answer this 27.162, you would say this is about 27 million. Okay, that's a very important thing.
People.
Yeah, people. Dollars, whatever. Next, if the population grows at this same rate, what year will it reach 30 million? So this is like the last one. We have already graphed it for you. You would go at this point, all you know how to do is graph the given function and the function. Notice, you're not going to graph 30 million because your y-axis is in millions. So you're going to graph y equals 30. And there's our two functions. The red one is the exponential one, and the orangey one there is our constant function of 30. And there is your point. And we would answer in 67 years is the first part of the answer. Okay? And now we need to figure out in 67 years, the question is when will it, not how long will it be.
In what year?
In what year? So 67 years after our start, that would be 2,000 years, the year 2067. And that is actually the answer to this question. Okay? All right. Next problem. Geologists and archaeologists use carbon-14 to determine the age of organic substances.
The amount from 1 kilogram of carbon-14 that remains after X years can be approximated by this function. Estimate the amount of carbon-14 remaining after 2,000 years. Now the number 14 in this problem is not what you put in anywhere, so don't think that that's an important number, okay? What we want is the remaining amount after 2,000 years, and this is going to tell me how much is left.
Yeah, and that's 2,000, and this problem is not the year 2000, it is after 2,000 years have passed. So that is actually our x. How much time? So we're m of 2,000, which is 0.99988 to the 2,000. And we get that to be approximately 0.786. And the important thing of that is that that is a percentage, and we need to answer properly. We would say about 79%. And here's our graph. And if we go over here to about the year 2000, this is 2500 down here, 2000 is about right here, and you come up, your point there corresponds pretty closely to about 79%.
Okay.
And the last problem, this is a cool one. Those of you that get into calculus down the road somewhere in your life, you're going to love this function. It's called the logistic model. And it has a graph that looks like this. And all that we really are trying to figure out is graph the function. So we want you to properly graph this in your calculator and make sure you can get it to look like this. The scale that we used is 0 to 50 for x and 0 to 120,000 for y. All right, so use that scale and first of all see if you can get this. Now the question, finding the upper limit. Doesn't it kind of, Ms. Miller, look like it kind of flattens out somewhere there?
Yeah, it does.
So what would we do? We would probably just start plugging in big values for x, right?
So we plugged in 50 for x.
Oh, by the way, we have to use x here because our function in the calculator can only use x. Notice it's used a t in the problem, so we're going to use x though.
So if you plug in p of 50, you get 999.99999. Wait, is it 9? Wait, I made too many nines.
Yeah, there we go. 99,999.999. Pretty darn close.
Really close to 100,000. If you keep going higher, it'll just say 100,000. If you notice, that's our numerator.
So in the logistic model, what is really cool is whatever there's at the top, that is your upper limit. It'll never get bigger than that, and you'll do a lot more with that in the future.
All right, here's your last ET problem. These are calculator problems, but you must show your substitution and set up for credit. So, what you need to send us is 1 new thing you learned, be specific, 1 good question, 2 old skills that are important to recall, and don't forget to bring your entrance ticket to class.
We love you. Have a great day.